Yo, what up? So this is the conclusion of our Odyssey in differential equations, and we're going to talk about microlocal analysis, D modules, and categorical resolution to just kind of look at swirling phase spaces and cotangent bundles, and we're going to try to visualize rays of singularities that propagate like light cones. And yeah, so that's kind of the, phase space. Essentially, we get back to the phase space as the reality itself. So yeah, I'll try to guide you through, this recursive kind of jet space. And it's kind of ironic, that I'm like jet bundle, right? And I'm stuck in phase space trying to resolve singularities. So if this video gets too meta, right, well, we can just kind of prolong it into an alien derivative and hope that the Stokes phenomenon doesn't flip the sign on our sanity. Okay, I'm done with the jokes. So singularities aren't failures, all right? That's kind of what we're going to talk about. Most people are like, oh yeah, singularities are these artifacts or whatever. It's like, no. They are geometric objects that live in phase space, all right? And we're going to lift from position space two cotangent bundles, and we're going to algebraize everything with D modules and discover that the true solutions to differential equations are actually topological sheaves in disguise. And this is where we're going to have a nice kind of, introduction to the fact that analysis, algebra, topology, and even quantum field theory kind of collapse into this kind of one, beautiful and at the same time extremely terrifying and spooky picture. Okay, so we're gonna get microlocal today. Okay, and in last episode we lived on jet bundles, right? And these are partial differential equations that are manifolds and solutions to integral surfaces. It's very beautiful, a beautiful picture. But until we get singularities, so remember going back to the tensor, to solving differential equations in tensor fields, we get these kind of weird caustics and shocks that make tangent planes themselves in the jet space, vertical. Okay? So the function itself will break symmetries, or it'll just break, the function breaks, sorry, but the geometry itself doesn't. Okay, so then we kind of need to relax our idea, just kind of like how the formula itself broke down in our very first episode because of chaos theory and all this stuff, okay, nonlinearity and whatever. So we just said, okay, well then let's just define a weak derivative. All right. So what we're going to do here is the solution to this problem is we're going to lift everything to something called a phase space. And the phase space, again, this is a cotangent bundle on the manifold in the configuration space, right? It's a cotangent bundle, and position and momentum become coordinates on this phase space, and singularities are going to be, we're going to turn them into well-behaved geometric objects. So cones, rays, and Lagrangian submanifolds are also going to be something we'll introduce. But again, the microlocal viewpoint will resolve what classical analysis typically calls a failure, okay? And the most important fact from this is that almost every major breakthrough in modern partial differential equation theory since the 1970s, with Hormander, Sato, Kurosawa, Mechbud, Ekale, this is all built on the phase space philosophy, okay? And so that's really what you can take away from all of this, all right? The microlocal viewpoint is allow us to then algebraize the structure of phase space with D modules, and then, again, have a nice Riemann-Hilbert correspondence and sheaves, okay? So, microlocality, okay? What is microlocal analysis and what is a wave front set? The easiest way to think about this, sorry, that was my phone. The easiest way to think about this is that smoothness is a local property. Classical smoothness is a local property. So, microlocal smoothness asks then, in which direction is the function singular? Now, that might not make sense at first. Like, okay, it's a singularity. What does it mean a singularity has a direction? Okay. Well, let's define something called singular support. So a distribution is said to be singular at x if it has no smooth cutoff function that makes its Fourier transform decay rapidly. Okay. And what that essentially means is that we can define something called the wavefront set. In the wavefront set, the WF of U is a submanifold within the cotangent bundle. Okay, and it collects the pairs of x and I'm sorry, it's technically a subcotangent. It's an element. Okay, it's within the space of the cotangent bundle. Okay, and U is non-smooth at x in the direction of C. All right. And so what this allows us to do is then talk about a crucial theorem by Horamander in 1971 that he proved for hyperbolic operators like the wave equation. Okay, and what is a hyperbolic operator? Again, it just has to do with the way that the PDE is built. It's second order in time and space. Okay, and in general for hyperbolic operators, singularities will propagate exactly along something we call by characteristics. And this goes back to the idea of caustics and light rays, that were, these blow-ups in the WKB approximation where the frequency got too high, right? So the Hamiltonian flow in the phase space is the bicharacteristics, okay? And that's why sound and light rays exist, because they are the tracks of singularities themselves. And just to show you how much of a breakthrough this is, you have to realize that if, let's say we move a singularity position, through this function, okay? Or along, the singularity position is defined by this Heaviside step function, okay? It's a jump function. And as you can see, the Fourier transform, again, because it's said to be have singular support, right? Because we can't make a smooth cutoff of the function, so it's 0, or the Fourier transform decays to 0, all right? And that's essentially what we get. It follows this envelope roughly. I'm not calculating it precisely, but it should converge to that, okay, analytically. So this is for, a Heaviside distribution. Again, this is a wavefront set in phase space. Going back to this, right? The wavefront set collects these pairs where U is non-smooth in the direction of C, okay? And this wavefront set is particularly given, okay, at that singularity point. All right, and again, we can look at, let's see, I don't know. Let's look at a corner, right? And that's what a corner looks like, a corner function, right? Or a cusp. And then we can look at, let's see, a delta function, or just I guess technically it's normal distribution, but a delta function. Okay, think of this as a delta function, right? And also we can do this for for a function again with a singularity itself, right? A function with a singularity, it still works beautifully, and there's no analytic solution to it. But again, the Fourier transform decays to 0 and it disappears. And then the last one, we just have a smooth vertical line in phase space with singularity. Very beautiful, okay? So as you can see, and again, probably gets the same, so I'm computing it in real time, so you don't have to take my word for it, all right? Now, again, this is why, again, I hope you understand what's happening here. Ray optics works in high frequency limits, okay, because singularities follow geodesics in phase space. The geodesic itself is being encoded in phase space. All right, and if your function has a jump discontinuity, the wavefront set. Okay, so let's say let's go back to the discontinuity here. If the function has a discontinuity, then the wavefront set is basically saying, I refuse to be smooth in every direction except the boring, p equals 0, 1. All right? And that's kind of that's what the rebellious function is kind of, inscribing onto the cotangent bundle. Okay? So now that we kind of have this idea, let's go to algebraic analysis of D modules. All right? What is a D module? Well, a D module is a ring and again, we're not gonna differentiate functions anymore. We're just gonna talk about the differentiators. Okay, the differentiators. Now, a ring, a D module, or a D sub x of differential operators with smooth coefficients and non-commutivity. Okay, and this is what is said to be the Weyl algebra. Again, this is like a raising and lowering operator in quantum mechanics that's defining that algebra, right? Because the commutation between them is unity. A linear PDE system, course. Actually, I don't even know if I covered that in the initial conditions. Correct me if I didn't. Okay, but a linear partial differential equation system is a left ideal. Okay, it is said to be a left ideal of the D module. And the module itself, or the system, is the quotient module of the D ring of the differential operators, quotiented by the ideal. All right. So that basically means that we're going to encode the system within some module M. All right. And when solving the equation P acting on U equals 0, okay, this corresponds then, okay, to finding the home set, okay, the set of homomorphisms of the linear differential operators, or defined by linear differential operators of, M comma O, where O is the function space itself. Okay, and why is that important? Because this will allow us to define something called the characteristic variety. What is that? Well, the characteristic variety is said to be a variety of a characteristic, okay, and a characteristic that is a variety. I'm just joking. So it just has, a matrix has eigenvalues, right? So the D module is just kind of this, it's a subset of the cotangent bundle on some x, where this is the set of points where the symbol, the highest order term of, operator vanishes. Okay, so it's kind of like, again, getting the polynomial or the characteristic polynomials of, some particular operator, right? And if we plug in the operator into the particular, so again, if we plug in an operator into the characteristic polynomials, that gives us the eigens, that encodes the eigenspectrum, encodes the eigenvalues. Okay, so that's what a characteristic variety all it is. Okay, it just allows us to do the exact same thing. All right, the dimension of the characteristic variety is never small. It is always at least the dimension of the manifold we're taking a characteristic variety of. All right, and systems where this dimension is exactly the dimension of the manifold are said to be a holonomic. Okay, and these are integral systems of the algebraic world, because it's, guess what, where we literally solve this equation, okay, and find the Hom set. Okay, so again, the algebraic world, including all special functions from level 1, or from the first video. This was originally supposed to be a 7 levels of differential equation series, but I was like, and I was gonna condense it into one video, and I was like, there's no freaking way. So I was like, I'm just gonna make the 7 episodes, but that's the lore. But yeah, so again, Bernstein's inequality allows us to say that if the dimension is greater than the dimension of the manifold, there's always at least it's always at least the space dimension that we're applying the characteristic variety of it. Okay, and again, when the equality holds, we get holonomic modules. Okay, the modules themselves are said to be holonomic, and these are integrable systems of algebra. So we got hypergeometric, Bessel functions, area functions, Poinlevé. I don't know how to say it, but again, all the special functions that we talked about from level 1 that I ranted about, or from episode 1 that I ranted about, they're all holonomic. Okay? So that's why the special functions themselves, the hypergeometric functions that include the Bessel, the area, the Legendre, everything, they're all holonomic functions, and that's why we can solve them, okay? Because of their characteristic variety and our good friend Bernstein, which allows us to talk about stuff. Okay, so let's look at this. All right, so this is a hypergeometric function. All right, and this is said to be the characteristic variety. And I'm going to turn off the Lagrangian just so you can see. And Jesus Christ, this looks kind of messy. Sorry, but yeah, these are kind of the this is a hypergeometric, and we can adjust these parameters as well. And again, show you that again these curves that are being traced here are from the characteristic variety of the hypergeometric equation. And as you can see, it's quite simple actually to just solve them. All right. So given some parameter A and B, okay. And these branches, or let's take a look at what's happening here. The characteristic variety is the zero set of the principal symbol, okay? And it would be a Lagrangian. This is a Lagrangian, or let's show Lagrangian. The Lagrangian surface itself, as you can see in phase space, is where the dimension is equal to the dimension of the manifold itself that we're looking at the D module from, okay? Or that we're encoding into the D module. And again, it's repeating for some reason. So, but as you can see, I'm computing this pretty fast. Holonomic varieties are really rigid. And they're so rigid, they almost determine the module. So this is why special functions are special, because they're the minimal, most symmetric structure, or most symmetric solutions in the algebraic category itself. All right, and so we can see branches, or this is the branches, the singularities, the real versus complex parts. It's all encoded within this characteristic variety. All right, and again, this is the branch 1. Okay, that's the first branch, and this is the second branch. I can't hover over it, and then this is the Lagrangian. These are the Lagrangian points, or the Lagrangian densities. Okay, and this Lagrangian surface then tells us everything that we need to know about these particular polynomials. Okay, or not polynomials, these D modules. Okay, so we can look at different ones. So let's look at the Bessel functions, and the Bessel functions look very nice. And that's the singular point again. That's 0, 0 for a Bessel function. And we can see again, it's just beautifully encoded within this characteristic variety. And for different choices of for different choices of A and B. All right, so we can change A to be much more kinder to us, and B. These are just parameters for these characteristic varieties. I encourage you to come play with this. But I mean, these are Legendres, and then these are the characteristic variety for the area equations. Okay. So again, what are we doing again? What's the whole point? The whole point was to define a ring of differential operators, and we just quotient it by the left ideal of that ring. And that's the quotient module. If we solve the equation where everything maps to 0, we find the Helm set, and that's the function space. Here's the function space. Okay. Fun. And this is the area equation. As you can see, the branch here, all of the branches are well defined. It's perfect. Okay. So let's talk about the Riemann-Hilbert correspondence, which is really spooky. All right. So this is like a grand unification between analysis and topology. So we'll talk about regular singularities, and these are said to be locally consistent sheaves. Okay. And a sheaf is just a bundle of vector spaces over the manifold minus the singularities. Okay. That's all a sheaf is. And so regular singularities again are said to be locally consistent sheaves over a punctured space. All right. And the Kashiwara Mebhut in 1980 told us that the equivalence between regular holonomic D modules and perverse sheaves it can be basically is defined by some these are topological objects that are constructed from the geometry of the singularities themselves. And what this allows us to do is just say, this means that if we calculate the cohomology of a differential equation with analysis, this is equivalent to calculating the intersection cohomology of a geometric space topology, and so they're kind of like equivalent. And this is the Riemann, or this is the correspondence, okay, that was discovered in 1980. Okay, so the translation of this to, I guess, in a more intuitive sense, is that the analytic solutions, okay, remember this is a differential equations video, so the analytic solutions of your partial differential equations are secretly the intersection cohomology of a geometric space. Okay, great. I'm glad that clears it up. So this basically just means that analysis is equal to topology in disguise. And that's what this is saying. Right? And this is one of the deepest results in 20th century mathematics. And again, this is 20th century mathematics. Nothing has changed. Okay? And this allows us to bridge, Sato hyperfunctions, Bernstein modules, the Bernstein modules, the characteristic varieties, and, the perverse sheaves and mirror symmetry. All of these things are, we just bridge everything. Now let's talk about resurgence and alien calculus. Let's go back to the divergence, or the Borel, or renormalization. The thing that defines renormalization, which is the Borel series and Borel transforms and all this stuff. Okay, so we can define in Jean Nicole in 1981 introduced something called resurgence theory. Resurgence theory. What we can do is take the Borel transform of a divergent asymptotic series, renormalization, and the result is an analytic function with singularities in the complex Borel plane. All right? And these singularities, again, what did we say about singularities? They're not obstacles, right? They're the reason we have light rays and stuff. So they contain these non-perturbative, information about, instantons. Okay, that's what, and again, instantons, why are they important? Because they're like these solitons that don't scatter or anything, and they, help us, solve Yang-Mills theories. Okay, so, basically, so again, the Borel plane tells us take a divergent asymptotic series, apply a Borel transform. You'll get analytic functions of the complex plane with singularities, and these singularities will encode a new non-perturbative physics with instantons and tunneling and all this stuff. Okay, and the alien derivative, then we can define something called an alien derivative or alien calculus. This allows us to measure jumps around singularities along Stokes lines. Okay, and we can then form a Lie algebra with this and quantify the Stokes phenomenon exactly. Okay? And remember, we use this as a mathematical tool to solve differential equations. And so this is where it comes all back together, because these alien derivatives form Lie algebra, quantifying the ambiguity of the resummation, and they just encode that Stokes phenomenon. Okay? So what we can do is we can choose a series. So, here's an Euler series that we talked about earlier in the very first episode of the series. We also have a quantum electrodynamics series as well. Here's a Borel plane for perturbative quantum electrodynamics with a divergent series. And then we can also look at an anharmonic oscillator with a divergence series. Again, here's a singularity. There's a singularity. There's omega. Okay, the alien derivative, and then we can also look at a double well. Potential. Again, there's a singularity there. And again, this is the real part of zeta and the complex part of zeta for the Borel plane. Okay. And what else was important about this? And here's like a custom one. Okay, I just put like a random whatever, and then we can do a Borel transform phase to define the alien derivative. Okay, so it's kind of fun, and we can we can do this for any level that we are truncating the series. Nothing really changes. Again, nothing really changes. It's computing. All right. And we can change where the singularity point is. Okay. Oh, sorry, we can change where omega is, right? And again, it's still defining the alien derivative wherever. Okay. We can also show the Stokes lines themselves. And is it showing? I don't know where they're showing. Hello? Show Stokes lines. It might not be working. Yeah, I don't see them. But anyways, yeah, that's kind of disappointing. I wanted to see the Stokes lines. Or am I able to compute any? Are there any Stokes lines? Okay, you know what? I'm gonna leave this for the people in the YouTube that want to correct me. Okay, and correct all of my mistakes. Okay, but anyways, that's the alien derivative. Okay, it's simple, right? We're just taking a Borel plane, and that's what resurgence theory allows us to do. We study the divergent asymptotic series that are physically meaningful, and finally, we run into quantization and topological quantum field theory. This just again tells us that we can close this entire series with the idea that phase space itself, the cotangent bundle acting on some manifold which defines a phase space, is a symplectic manifold. So functions get replaced with operators. The Poisson bracket, will implies a commutator or quantization, and so partial differential equations will become the classical limit of quantum theories. All right, and so this is the entire classical mechanics, and the symplectic geometry will be preserved under quantization, under geometric quantization. Okay, so topological quantum field theories that were talked about with Atiyah in 1988, and with his index theorems and other ways of quantifying these topological invariances. In TQFT, observables depend only on topology, right? Not metrics. So all the invariants that we found, right? Indices. That's the right word, not indexes. Who says indexes, right? Stupid American. Chern numbers, right? Or, Euler characteristics are, TQFT, partition functions, okay? And again, these invariants we discovered they're all observables. Okay? These are physically observable. And so, it just shows the power of topological quantum field theory. And, this is important for real, the Majorana chip, the big chip, I think is it Google or Microsoft? I don't remember. I don't really care either. But the Majorana chip, I'm going to look it up later. I do care. But the Majorana chip that, for Google's quantum computer, I don't know how many qubits they have. I think they have like 6 or something. But those chips are topological, quantum systems, okay? And they're Majorana modes, which just means that they act like Majorana fermions. They're like these quasi-fermions, right? And so, again, the work that's done here in the topological quantum field theory is it's applicable. It's applied, right? This makes computation of, particular field theories and behaviors that we should be able to observe and see in the real world. This is mathematical technology for us to use, okay? So, again, thank you for going through this entire series with me, and hopefully it was valuable to you. So let's recap this episode again, as we always do. The microlocality allows us to lift the singularities to a phase space. D modules just algebraize everything, and it's like the equivalent of, eigenfunctions and eigenvalues, but like, whatever. We get it for modules instead. We can solve entire characteristic varieties of, differential equation of polynomials. The Riemann-Hilbert correspondence will allow us to topologize algebra. Okay, so D modules algebraize, Riemann-Hilbert topologizes, and then resurgence theory allows us to extract non-perturbative truth, and physicality from, and again, quantization. Quantization just, I guess, makes it quantum. Okay, so we've gone from jet bundles to preserved sheaves, to perverse sheaves. Again, to topological quantum field theory, and this makes analysis again becomes topology becomes physics. So again, thank you so much for prolonging with me this far. And if you're still watching, congratulations, you're now holonomic, and experiment with these interactives. And I'm gonna publish this on GitHub, and like, maybe one day I need to debug some. There's like a short that I left out there where I had a vector parallel transported, and it like, had a Chern number associated with it on accident. I think I like doubled the phase or something. Whoops. But anyways, I need to debug that. But yeah, so like, subscribe, and share your favorite singularity. Next time, applications, or maybe we'll quantize something, or actually I know exactly what I'm going to do next time. So stay in touch. All right.